Welcome everyone to the second invited talk today. So it's my pleasure to introduce Sebastian Riedel. He got his PhD from the University of Edinburgh and is a student of Evan Klein. And then he, among other locations, he was a postdoc with Andrew McCallum, and then latest he joined the University College London. But he's also a researcher at Facebook AI and also an Allen Distinguished Investigator. He's well known in his area of NLP, has done a lot of publications, and I'm happy to hear today something about open and closed book machine reading. So the floor is yours.
Thank you so much. Thanks so much for the kind words and for inviting me generally. I'm really unhappy to not be there in person, not just because I have family close by, but also because Bamberg seems really nice and it's much nicer to be obviously at a conference with people. But I still, happy to be here. As I said, or as Andreas said, I'll talk about open and closed book machine reading. Before I start, I want to give like a very, very brief, overview of what Facebook AI research means, not so much to advertise, but more to indicate that what I'm actually doing here has very little to do with the Facebook product, and it's essentially sort of core fundamental research. And that's because I'm part of not just Facebook AI, but what is called Facebook AI Research, which is sort of the AI, or was the original AI research arm of Facebook created by Jan LeCun back in 2013, who probably most of you will know anyway. So I'm not going to talk much about that. But what I do want to talk about briefly is just the vision or the mission of FAIR, which is generally to advance the state of the art in AI through open research for the benefit of all. So there's actually nothing really related to Facebook in that mission either. And while we do work or some of our work gets used in Facebook products, we're not told to do that in a way. That's something that makes sense in many cases, but it's not our mandate. And that also relates to our values that we really push, and I think make us stand somewhat uniquely in the industry context, at least. So like, we're completely open. We publish and open source pretty much all the work that we do. And we're completely free to do whatever we like. So like, all of the researchers at FAIR, they do whatever they think is most important. We collaborate a lot with internal and external partners. So I have PhD students that we co-supervise with people in academia. And obviously we focus on excellence, and that's something that I guess most people focus on, but we also focus often on scale, because that's something that obviously we can do with the resources we have. And that's really just to set the context for what I'm going to talk about next. In case you have questions about how is this useful for Facebook, or how it is used right now in Facebook, the answer usually is maybe in the future, and there could be possibly good use cases for it. But just in the same way that like any kind of research in AI is probably useful for Facebook and Google and the broader society at large. So with that in mind, let's actually go to the core topic. And I like to start usually by giving a small origin story of human reading and writing, and then put this sort of into the context of machine reading. So you can look back maybe to about 3000 before Christ, when there were kings that had questions such as, how much does my minion Rick owe me? And other minions who would tell them basically that John owes the king maybe 100 coins, and that John brought the king 50 coins worth of wheat already. So John really doesn't owe the king 100 coins, but 50 coins. And that John's grandson Rick paid back the remaining 50 coins. So at this point, the answer is like, no, there's nothing owed at this point. Problem is that this kind of knowledge usually is distributed in space and time. So these minions might be in different places of his kingdom, and they might observe that in different times of his reign. So really, it's very hard to communicate this efficiently unless you write it down into some kind of document. And that's really basically how reading came about in a very short description. Now, this obviously has been the foundation for a lot of human progress, in particular in science, where we talk about more interesting things than deaths, and where I guess the free sharing of ideas through language written down in text and articles has been really, really critical. But I guess what we've seen in the last sort of decade, 50 years, 20 years, let's say, is that this kind of data has exploded, in the sense that now a simple question such as how much does Rick owe me will be really hard to answer, because there's just so much information and you need to scan through this to come up with answers. And that's where essentially machines come into play, and where we say, let's get these machines to read all of the documents for us such that they can answer the questions for us, and we don't have to do the reading anymore. So let's get this all somehow into the machine, and then let the machine answer this question directly, so that we don't have to. I guess one of my main research questions has been for a while how this can happen. Like, how can machines do this type of quote unquote reading? And why do I think that's important? Well, I mean, obviously, as I mentioned, it's a foundation of science to be able to understand large bodies of text. And so if we can partly automate this, then we have a shot at better science. We also have a shot at better fact checking, and you can see how that is somewhat related to Facebook at this point. So if you have a question about a particular statement, can we help fact checkers, say, to answer that question or to test that claim by having the machine pre-read all of the web to figure out relevant information and present it. It's also interesting in the context of bots. So like a lot of the bots that you look at in practice, they are very task driven. They help you to do a particular task. But now we're also starting to look at bots that know things, and they can help you, tell you things about things, to inform you in a particular context about the world, or just to have a more informed chit chat with you. So being able to read massive amount of text is critical for that as well. Another thing that we're interested in particular in FAIR London, is how reading can help you to make better decisions. So we have researchers in London, Tim Rockteschel in particular, who's been looking at reinforcement learning with a view of using, I guess, Wikipedias or game wikis as a source for helping the agents to better solve a particular hard task. And you can imagine how maybe similar things are useful when you have a repair robot that has to repair a new bit of technology. It will probably have to read the manual for it, and it has to probably read up upon the particular details of this whole machinery and the context. So it's useful as well in that context. All right, so how can you go about this? I think for a long time, sort of standard go-to solution would be for humans to write machine language, such that the machine then can answer this question directly without any kind of translation between what humans write and how a machine can operate. So concretely, maybe in the case of the original questions about debt, I mean, it seems quite natural to write down a table with debts and then calculate these things relatively easily through something like Excel, and you don't have to do much reading at that point. That's a natural, I guess, place to, rather than writing in human language, write in something that a computer can understand. There are other efforts where, for example, we started to produce or take our factual knowledge that we have and convert it somewhat manually into knowledge graphs such as DBpedia, Wikidata, and so on. So that's a reasonable way to do it, and these resources have been becoming bigger and bigger. And then, like, for more, say, complex content that isn't just factual, or that isn't just sort of first order, or that isn't just factual about facts in the world. You can think about more complex logical formalisms that capture meaning and that might enable the machine to work with that directly. So that's one way, like humans just directly operate in this space. Clearly, I mean, that's kind of doable for tables and a particular type of data, say debt. But the minute you talk about language and you talk about more complex language, it is not super natural and easy for humans to write things in machine language. And so for a long time, I think research in this field has, I think, what I call done machine-machine translation, where the natural language that is originally present is translated in some kind of automatic way to a, say, knowledge graph. And so you basically, anytime you get new natural language in, you somehow translate this to a graph and you integrate this into a bigger graph until you get a big knowledge graph. And then it's that knowledge graph that the agent or the machine is operating on when answering the questions. And that's often much easier than directly operating on the text. By the way, I don't know, I have done very few Zoom talks, and so I don't know how this best works, but obviously if there are any questions, I'm also happy to take them as we go. I don't know how feasible that is or how common that is, but generally I'm happy to take questions. So there's a way for you to do that, and I'm happy to answer. All right. One way I like to describe this setting is as a form of what's called closed book machine reading. And I call this closed book machine reading because this kind of graph is created a priori before we actually have specific questions. So there is this sort of internal memory, this graph, that we are filling up and populating for the machine. And this internal memory is structured in a way optimally for the machine to retrieve useful information and to answer questions. But this process is happening before questions are asked. So once I get a question, I cannot go back to the original books, to the bits of text that the graph is used to produce, but I have to use that graph for it. And so that's why this is a form of closed book machine reading. Now, this has been, I think, until say 2016, this really has been the dominant approach of how to think about machine reading and information extraction on knowledge-based population. And so I like to give this example of a DARPA program grant that started around 2006 that actually I was a part of back in the US when I did my postdoc. And this program grant was literally called Machine Reading. And it had this really nice picture to visualize, I guess, the aim and the whole idea of machine reading. And it's this robot that obviously reads a lot of books. And while the robot is reading these books, it is writing down a formal representation of that book. And that is the sort of reading process. And I think good progress was made in this domain for quite a while, but there were a couple of issues that I think weren't really addressed even with the progress that was made. So generally, maybe not so much for simple factual claims, but for anything that is a bit more subtle and deep, it is not obvious how to fit human language into these kind of symbolic representations. And people will spend a lot of time just arguing about the best way of doing this. And a lot of research was just about that before it even got started into the actual translation process. So that's a very hard question. And I think probably maybe impossible per se, but I mean, that's an open question. And as I mentioned, it's kind of hard to agree what that language, that computer language should be. It's hard to get supervision data of this type. So basically you need examples of books or text and the logical or symbolic representation of the meaning in that text. And that requires having relatively expert annotators to go and write down this annotation, which is a noisy process, which is expensive, is hard to scale. So that's another critical issue with this approach. And then I think it's really hard to, and that's I think a general issue with the closed book idea. It's really hard to know what you should remember and what you should in a way cut out when you read the text and integrate it into your knowledge representation. Because maybe you know a couple of use cases in advance, but then there are always sort of new things that happen. And when they happen, you have to go back and start to improve your representation and add more detail to it. And it becomes more and more cumbersome to do that. So these are all issues that to some extent were, I think, recently addressed much better. And before I get there, I'm just going to give you a quick overview of the remainder of this talk and how this relates to what I just said. So first, I'm going to talk about unsupervised neural machine comprehension for open book readers. So I'm going to make a case for why open book reading is actually a good idea and has been really the dominant approach in the last couple of years, and then show what problems are and how we can address them in that context. Then I'm going to go back to closed book readers, because if you look at how good these open book readers are right now, there's still a lot to be desired, and then nowhere near where we want them to be. So I'm going to ask whether language models can be, in a way, closed book readers and overcome a couple of the issues that traditional closed book readers have, and maybe also issues that open book readers have. And then I'm going to talk a bit about a hybrid neural open and closed book reader that we just developed this year that works really well and has a couple of really nice properties that I think are good to have. And then I'm going to, time permitting, look at a application, namely question answering briefs for fact checking, which we essentially, where we essentially use open book reading to help fact checkers to do their work a bit faster and more accurately. And then I will conclude. All right, so rather than thinking about closed book reading where some kind of internal representation is created a priori, we can look at open book knowledge, where pretty much similar to how you imagine like an open book exam in your class, where you're allowed to keep the books around and carry them around. And when there is a question, you have to find the right answers in the book, which by itself is a difficult task. And if you have access to such books, why not, right? So essentially the open book exam equivalent of closed book reading. And the way this usually works is that you do some kind of retrieval step first, where you find the 3 most, say, or 5 or 10 most relevant documents. And then apply to these documents what I call like end-to-end neural reading. Essentially a neural network that takes the input question and the input context, the ones that we retrieved, and then extract or produces from there the actual answer. And it was around 2015 where this became a reality due to, I guess, the sort of deep learning breakthroughs that people had there, and better neural language models, or sorry, neural recurrent networks, LSTMs at the time, that made this kind of made this kind of thing possible. I'm going to particularly talk about the most common type of question answering, or neural question answering, namely extractive question answering, where usually you have some kind of input text and you have the question, say, where did Tesla study? And the answer to that question is a span in that input text. So you don't have to generate something that isn't really in the text, like you don't have to make up words. The answer will be something in the text. I'm going to add or introduce like a tiny bit of notation just to be able to refer back to that later. And so I'm going to call the question here Q, and I'm going to call the context C, and I'm going to call the answer A. This type of reading, people I think even already by 2018, have to some extent, quote unquote, solved. So there was a lot in the news about robots on the benchmarks that we had, outperforming humans, putting millions of jobs at risk, which obviously was like a real exaggeration, because these models make a lot of silly mistakes that no human would ever do. So by far is reading solved. But there has been good good performance improvements and actual real progress. I think people sometimes get a bit cynical about this, but like if you look at where we were at that time and where we are now, I think it's clear that we learned quite a lot about how this can be done much more accurately and even robustly as before. But the thing I want to address here is not that these models aren't like so robust to say adversarial inputs, but in other ways, they're not really superhuman. And the main way in which they're not really superhuman is the fact that they need quite a lot of training data. So if you look at human performance on the squad benchmark, it's 91% accuracy on the squad benchmark. The machines give 93. But really, if you look at how much actual Q-C&A, like question, context, and answer training data the humans had to do this, there was very little. I mean, humans can read these after having learned language in various sort of other contexts, but without direct supervision on this particular task. Whereas the state-of-the-art models, they require something along the lines of 100,000 training instances to get that kind of performance. Just quickly, there has been, I think, just even in the last, say, couple of months, quite a bit of progress on zero-shot or few-shot learning that dramatically reduced this this number. Really exciting work also coming out of Munich, for example, in doing this with much less data than the OpenAI GPT-3 models do. But still, actually, the ideas that we find in this sort of few-shot learning are actually somewhat related to what I'll talk about here. So I think it's interesting, nevertheless. So this research is in a way trying to figure out how we can reduce the number of training instances we need to do accurate machine comprehension or extractive question answering when you're given an actual input context. Oh, sorry. Maybe this is good for a break and to slow things down a bit. Sorry, I have to go through this again.
Take some time to display.
Yeah, it does, yeah. But anyway, yeah. So this work is essentially about making a small step towards using less data and maybe getting somewhat similar performance. We're not quite there yet, but I think we made good progress. And so this is work by primarily led by my PhD student, Patrick Lewis, who is one of these FAIR PhD students that actually work part-time at FAIR and part-time at University College London, pretty much on the same topic, freely and openly with people at UCL and FAIR. And so this work is one such work that came out of this collaboration. Just to give you a sense of how supervised question answering works in this context, usually there's some kind of annotator that creates these Q, C, and A triples. And often the annotator creates those by seeing a given context C, and then from there on, maybe choose a good candidate answer and generate the question that produces that answer. And then this data is given to the model that learns how to produce an A given a Q and a C. So that's easy enough. The main idea of unsupervised question answering is that we replace the annotator with a model that produces this, this training data for the actual Q, C, and A, the actual Q and A model. And due to recent progress in unsupervised machine translation, we can actually build a model of this kind of data generation process that doesn't require annotation. And I'll talk about that in a few slides now. So roughly the way that we go about this is that we take a given context and we choose automatically, and that's not too hard, a given candidate answer. And answers have very regular structure. They're often noun phrases, often entity or named entity noun phrases, but generally, actually, in most of the cases, noun phrases. So we have a way to identify those without actual annotation. Note, we actually might need annotation for noun phrase extraction. So there is some amount of annotation here still, but it's not question answering annotation. But just to keep in mind that it's very hard to do something that is really, really not annotated at all. But the kind of annotation that, or the task that we're aiming at doing, for that, we don't have annotation. And now that answer, we mask in the original context. So we create this, what is called a closed question, where the answer is blanked out and you need to fill it to help Tesla leave for question mark, where he was to study. So at that point, we almost have a question, but not quite a natural language question, which is the kind of thing that we need for question answering. So in a final step, we then translate, and we actually literally use machine translation technology for doing that, translate the closed question to an actual natural question. And yes, so this is machine translation. So now in this reduction from unsupervised or question answering to machine translation, I guess we just have to make sure that we're really not using any kind of annotation for that translation process either. And luckily, there has been work on doing this. But before I go there, I quickly give you a bird's eye view on machine translation to the extent that it's necessary to understand what I'm doing here. So machine translation model today, they more or less look like this. There is some kind of encoder for the input language. And this could be a transformer encoder, or it could be an LSTM encoder, or whatever you fancy. And then there's a decoder that generates, based on the encoding of the encoder, that generates the actual, in this case, English text. And usually you have supervised data for these two sides, and then you just train these encoders and decoders end to end through backpropagation and some form of gradient descent. If you do this unsupervised, and this is work based on Lamper et al. In 2018, basically what you're doing is you somewhat generate the training data automatically in a bootstrapping process. And in this bootstrapping process, there are two components. One is a noise generator, where you say, look, there's a very simple way of taking, say, English outputs and producing, I guess, noisy English outputs from it, say, by just moving along words. And while you cannot use this to train the German encoder, you can use it to train the English decoder and the English encoder, which we need for the other direction. So you have these blue German or English encoders and English decoders, and you teach them to translate from noisy English to noisy clean English. And that will help to at least improve, in this view, the English decoder. It will also help to improve the English encoder for the other direction. And then the other thing that you do is you have a possibly bad, possibly just recent, like very dumbly initialized actual translation model from English to German. So a model that takes an English sentence and translates it into a German sentence. And this might be a bad German sentence, like Jan Lekun gewonnen, den Turing avoid, but still it will help. If I use this pair now as training data, it will help the German encoder to learn a bit more about German and about the translation process. So you can do this now in one direction, but you can also do it in the other direction. So if you go from English to German, you do pretty much everything the same way. You build a German noise generator, and you use the model from the other slide, the German to English model to produce actual training data. And you just keep on iterating this. And once you do, you actually get remarkably good results. So on a couple of language pairs, unsupervised machine translation basically gives you supervised results. It works remarkably well. And this general idea also since then has been used for really interesting other problems, say translating language to, or translating between program languages, where you often don't have actual one-to-one translations or not big training data of it, but you can use this technique to essentially learn a Java to Python translator. Now, we use this pretty much, I mean, straightforwardly, and just frame the close translation task in this framework. So we have these close questions on the left-hand side, and we have the natural language questions on the right-hand side. And then we generate noisy natural questions, and we use a question to close translation, close question translation model to generate additional training data as well. And we iterate that just as before. So at this point, the application of that idea is very straightforward. And the only thing that you need is this training data, is unlabeled data for both sides. So you need unlabeled questions and unlabeled closed questions, which are really easy to get. You can see that this works in practice. So we have a couple of example translations where a closed question was relatively successful translated into a natural language questions. It doesn't always work. And so there's definitely noise in this process. So I think the last one here is an example of that, where really the meaning kind of changed. But nevertheless, it works remarkably well, we think. I love this one just because it sort of reminds me of Brexit and how I feel about this. But leaving that aside, let's look a bit at the results. There is a couple of baselines for not using any any QCNA training data, and then there are results for actually supervised models. And if you look at a human, you can say that they basically don't need QCNA data to do this task well. We implemented a couple of heuristics. There's a relatively complicated previous work that I won't go into, which gives you around 35% performance. And the approach that we present here gives us like 55, which is already better than a supervised logistic regression model for these 100K examples, but much worse than the state of the art. So there's still a big gap, but I think we already closed that gap quite a bit since then. All right, so now this was essentially a component of open book machine reading, the component that you apply once you have the documents that contain the right information. And if you assume you have these gold documents, then you can get these superhuman performance levels. But usually you don't have these. Like you will have a lot of documents and you have to find them actually. So there will be noise in the process, and you will need to probably retrieve quite a lot of documents before you can actually capture it, actually find the right documents. And at that point, you have a lot of noise in your input as well. Just to give you a numeric view on this, if you use or have to search in all of Wikipedia for the context that answer the questions in standard benchmarks, you get about 46% accuracy compared to having the actual single correct paragraph where you get about 93% accuracy. So there's a big gap. Now, we have been making a lot of progress. I don't have a easy way to point. So you see these two peaks and these two hills here. One of them I'd say is open book. So we have actually done a lot of progress in open book, and we're sort of going further and further. But it's still not clear to me whether this sort of open book idea of retrieving the right documents and then answering questions based on these documents is really the best idea. And then we started to wonder, maybe we should go back to closed book, because clearly like humans can do this. and it can work really well. And maybe we just haven't done it in the right way. So one of the things we started to investigate is like how we can use sort of modern neural methods to do essentially closed book reading. And this is work which we published last year at EMNOP, which I, in this context, would describe as language models as neural closed book readers. And to make a bit more sense of that, you need to know a bit about what I call the Muppet revolution in NLP. It's very hard for me to gauge the room at this point and understand like how many people know about Muppets in NLP. So it's very likely that many of you know, and this might be very old news, but for the few that don't know this, like there has really been a big step change in NLP, like around 2018, starting 2018. And I like to think about this as the Muppet revolution. So before 2018, like a standard way to do NLP looked a bit like this. Say you want to do topic classification. You want to figure out Tesla was born in, you know, and the remaining context for that. What kind of topic is this? Is this sport? Is this politics? Is this technology? Is this, what is it? To do that, basically, you would have these word vectors that you estimate before by unsupervised training on a big data set. And these word vectors kind of represent the similarity, the semantic similarity between words. So each of the words would have some kind of word vector. And then these words would be, these vectors would be fed into a neural network. And that neural network would maybe say, oh, here, the topic is science, because the Tesla word embedding is the word embedding of a scientist. And hence, it's likely that this is science. So that works really well. But it can fail because in this case, the meaning of Tesla is somewhat ambiguous, and it really depends on the context what its meaning should be. So if you look at a context where you wrote Tesla was bought by so and so and so, you kind of know that this is not about the science Tesla. It is probably about the product or the car Tesla. In which case, doing the same approach as before is suboptimal because you're still using the same vector for Tesla that kind of reflects the fact that Tesla might be a scientist. So rather than doing that, and so the problem is here that the representation for Tesla in both of these different contexts is the same. So use the same vector regardless of whether you talk about Tesla in a, say, business context or in a science context. So today, this looks really different. And rather than having a unique but same vector for each word independent of the context, we have now different vectors for words in different contexts. And the way this sort of difference is happening is by essentially another neural network that uses the whole input before it produces the actual vector. So it has access to all of the context, and often these are called contextual word embeddings. It uses the whole context to produce the vector for Tesla, and then makes sure that it's a different vector. This approach is called a Muppet revolution because for some reason, like the first work in this line was called Elmo, and then the second was called Bird, and then people just got carried away and called them Big Bird and Ernie and Cookie Monster and whatnot. So it just became a thing, and now you kind of have to, or at some point you had to name your contextual word embedding methods, also called language models. You had to call them by Muppet names. But the impact of these models was really, really high. So state-of-the-art results on all tasks are now based on these models, and they have really been improved a lot. The way that these models are trained is via what I call pre-training with closed questions. So we don't have actual supervised data for these models either, for these word embedding models. Rather, we take sentences and we apply to those sentences these contextual word embedding, or what's called language models. And then in this sentence, we mask a couple of words and then ask the model to predict that word. So James was question mark in. The model has to predict born in this particular case. And this task, that's often called masked language model because it's sort of like a language model, but it inserts mask into the text that you need to predict. That's enough to train these models, but because the key is that you can do this with unlabeled data at large scale and hence learn a lot using just unlabeled data in that way. So you do this for a lot of instances, and after that, hopefully your model can do this kind of contextual word embedding approach that you saw in the previous slide. Now, I like to think about this as, and I think it is sort of officially called that way, as a form of closed book machine reading, in the sense that the neural network is this neural language model that we're building is the memory, and its parameters are the representation of the knowledge in the model. And you train it without knowing the questions you will have later on, just by going through text and turning every sentence into possible questions. But again, you don't have access to the actual questions you'll get at test time. So it's closed book in that sense. But it overcomes a couple of the issues that we've seen with sort of prior symbolic closed book approaches. Say, for example, we don't have to really agree on a particular schema or internal language of knowledge representation. The knowledge is stored within the parameters of these models, and the model can decide how to organize and structure it in any way it likes. So we use this essentially to ask questions directly as closed questions, and we came up with a bunch of closed questions that we then use to test different types of readers and see how well they predict them. So for example, we would ask them literally, where did Tesla study, by providing a closed question Tesla studied in. And we compared a couple of models in terms of how well they do it. So we have one sort of frequency baseline that kind of gives you a sense that this benchmark, or this, let's not call it benchmark, this probe in a way is a bit biased towards high frequency answers. So the frequency baseline chooses answers simply by returning the answer with the highest frequency that fits the type of the question. So you can do pretty well with that. You get a precision at 1 of 16.7%, which is not bad. We also looked at what I described earlier as this actual approach of translating the language into a graph. And that's a fairly difficult and convoluted multi-step process in which a lot of errors can propagate and emerge. And so the results that we got are actually really poor here, somewhat disappointing. We then did another version of this where we basically, in this pipeline of steps, really helped the model as much as possible by providing gold information. And then it was doing much better. And it was better than the so-called Elmo masked language model. So at that point, we thought, okay, that's good, a win for the, in some sense, a win for the translate to graph methods. But even then, we're looking at an Oracle translate to graph method, not the actual translate to graph method. But then when we looked at BERT, we saw really quite high performances just using BERT, which is one of these masked language models, using it out of the box. So that was pretty stunning for us and somewhat promising. I'll hedge on that in a second. This doesn't necessarily mean BERT knows, and there's a lot of controversy around like what BERT knows and what knows means, but still compared to, I guess, the results we get for like traditional translate to graph methods, we thought that was really quite striking. We also applied this to question answering, where we looked at a retrieve and read open book method and looked at its performance. And it was much better, but notice that this is an actually supervised system, whereas BERT was not supervised at all. Like we used this sort of zero shot, no supervision on actual natural language questions. and it did like quite well, given that it didn't have any supervision. In particular, when you look at precision at 10, if you look at the 10 best results and you see how accurate they are, or is the right solution in the 10 best results, then performance seems to get pretty close, which again, I thought was really quite interesting. As I said, it's not clear to what extent these models know and memorize in a way that definitely we do. Like I wouldn't claim that, but also in a way that more sophisticated translate to graph methods maybe would do it. So if you look at a few of examples here, the first one, it accurately predicts that Paris is the place where Adolphe Adam died in. But does it know that, or does it just know that essentially that looks like a fairly French name? And if you think about where French people die, then Paris is a pretty good bet. And if you're on Wikipedia, it's probably quite often that you're talking about famous people that at some point end up in Paris because that's where all this stuff happened. So does it know, or does it just guess really well? That's one big question. And clearly it sometimes guesses wrongly. Like JDK just sounds like something that is tech related. So it just produces like a reasonable set of candidates, but not the right answer. Also note that it has like common sense knowledge, not just factual knowledge. In fact, I think common sense knowledge is the much more common thing to associate with language models. Okay, so I'm running a bit short on time, so I'll use this. Maybe instead of doing this, I'll skip over the open and closed book model and talk a bit about recent work we did on fact checking using these ideas, and then I'll take time for questions. Okay, let me just get to this. Unfortunately, there are animations in here. Yeah, I was overestimating the speed I would have with not getting live questions. I thought it would be much faster, but somehow I ended up, being just as slow as usual. Maybe it's good. All right, I want to quickly talk about work that I find really exciting that uses this idea of open book machine reading. And we call this sort of fact-checking briefs. And this is work together with Angela Fenn, who's also a PhD student at FAIR. She's a PhD student in Paris as part of the CIVRE program, which I think is pretty cool, where I guess PhD students in industry or in academia can team up with industry partners, and FAIR Paris is doing this a lot. So Angela has been working on what I call open book reading for faster fact-checking. Just to go quickly through this, here the idea is that you have some kind of input claim that might appear on a platform like Facebook or elsewhere. For example, that the Earth moves closer to the sun every year. And the verdict for that should be false. And there's a big explanation for this, which sometimes involved actually calling experts in the field and asking them about it. All of these things fairly far away for current AI technology. And so, in fact, when you look at what fact-checking today or automatic fact-checking is doing, it either does one thing that I really don't like, which is essentially take the input claim and run a neural network over it, and then say, and maybe who said it. Let's say Donald Trump says this. Then it runs a neural network over it, and then this neural network says, no, this is definitely false. Most likely just because there's the Donald Trump feature that it has learned that means usually this is false anyway, which is just really what it is. But that isn't really what it should be, right? Like Donald Trump should be proven false, not because he's Donald Trump, but because what he said didn't make sense in this particular context. So in my view, that cannot really be the answer to doing fact-checking at scale. The other approach that people have is finding existing fact checks, like maybe somebody has already disproven this, and then match this new claim against this existing fact check. And that's much more promising, but obviously there are a lot of claims coming in that haven't been checked before. So at some point you have to check them, and checking them is very, very expensive. But we don't think that we can, at least at this point, do this like really totally automatically. I think there needs to be human AI collaboration to do this. So the way that we have been talking about this is in the form of human AI in the loop, where you have a fact checker that gets a claim and then uses a search engine to make a verdict on the claim. But in addition to that, the fact checker also gets what I call a brief, like a summary and like additional sort of prior information the fact checker can use to much more quickly enter the domain and understand what's going on, and maybe already have a sense of what the answer should be. And the way we've done this, or like our best performing system, is what I call a question answering brief, where given a claim, we have a model that automatically generates questions for that claim that one should look at in order to make a verdict on that claim. So for example, for the Earth moves closer to the sun every year, one question that it generates is, how does the distance between the Earth and the sun change over time from year to year? And then this model, or this question that we automatically generate, is fed to a question answering system, namely an open book reader. And it produces the answer based on evidence it finds on the web, and then extracts the answer to produce the actual sort of short answer that is necessary, and to summarize what's happening in the page. That's the high level idea. We have also other kinds of briefs, like one where you simply find passages that mention the concepts of the or passages that are found with TF-IDF based on the claim, or passages that mention or describe the entities that are mentioned in the claim. But what we found is that the QA briefs work best when we actually test them in crowdsourced fact-checking evaluations. So we did a test where we asked Mechanical Turkers actually to validate checks, so to validate claims. And we gave them a couple of options, like just the search bar, different types of briefs, and the generated QA briefs. And these QA briefs worked much better than just using the search bar only, and also much better than the other briefs in terms of the accuracy that these Mechanical Turk annotators had. It also reduced the time it took for them to actually do the fact check. Note that these numbers are still pretty low, so I think like you definitely don't want to fact check something at 67% accuracy, and using Mechanical Turkers, at least by themselves, is not enough to do this well. But seeing this improvement means that if we put several Turkers together, maybe they will do in aggregate even better. We also did this with volunteer fact checkers, like people that aren't professional fact checkers, but that also weren't paid to do this. They did much better. For them, the briefs didn't help quite as much in terms of accuracy, but it did reduce their time quite a bit. Okay, and with this, I'm ready to conclude. So traditional closed book machine reading has some shortcomings, which I tried to elaborate on in the beginning. Neural open book models can address them, but they require expensive annotation. So I spent a bit of time in talking about how we can make progress on unsupervised reading. Neural language models are promising closed book readers, and they outperform some of the classic closed book readers. But they also have issues, and I didn't talk much about this because I skipped that. We introduced one thing that I can really encourage you to look at on archive, retrieval augmented generation, which is essentially the best of both worlds, and we found this to work much better than any of the closed and open book readers before. And open book machine reading can actually help fact checking. And with this, I conclude here. Sorry for taking a bit more time.
Thank you very much for the very interesting talk. I think we learned a lot about closed and open reading.